Okay, we want to calculate the moment of inertia of a disk whose thickness is 2 centimeters plus 0.4 r, where r is the distance from the center. Now, clearly, as r gets bigger, this is increasing, and that means that the thickness of the disk starts out at 2 centimeters and gets thicker as you move away from its center. In every direction, it'll get thicker as you move away from its center. Let's also assume that the disk has a mass density of 1.7 grams per cubic centimeter. Question then is, what's the mass of the portion of the disk? First question I asked, just to get used to what we need to do here to calculate the moment of inertia. We're going to calculate the moment of inertia of the part of the disk, the little ring between 5 centimeters and 5.1 centimeters. That's a millimeter thick, kind of a millimeter thick hoop within this object. Okay? So we want a mass of the portion between r equals 5 centimeters and r equals 5.1 centimeters. And then we want to find the moment of inertia of that mass. Well, to find the mass, we know the density, we want to find the volume. If we find the volume of this thing, we can multiply by the density, we'll have the mass. Okay? Well, what I'm saying now is the circumference of this ring is about 30 centimeters. 2 pi times the radius being 5 centimeters, comes out, comes out close to 30 centimeters, okay? A little more than 30 centimeters. That's completely straightforward to calculate. Now what you have then at this approximate circumference, in the vicinity of this circumference, is you have a hoop. It's only a millimeter thick, okay? If you take a hoop a millimeter thick and cut it and straighten it out, you get a rectangle. Well, a rectangular object that's 1 millimeter thick. And we should understand that picture. Okay? So, or let's say 1 millimeter wide. Okay, so as I say millimeter thick, I want the thickness to be this dimension, the thickness of the hoop. And but then we have a 1 millimeter width between r equals 5 and 5.1 centimeters. So, the circumference is this. If we straighten the thing out, that's how long it's going to be. It's going to be this wide, and it's going to have another dimension, which is the thickness of the disk. Now, if r is in the vicinity of 5 centimeters, the thickness of the disk is going to be very close to 4 centimeters, as we obtained just by plugging in 5 centimeters for r in the expression for the thickness. That means that our volume is going to be approximately 30 centimeters by 0.1 centimeters by 4 centimeters. Because again, this thing forms something very close to a rectangular solid, 30 centimeters long, 1 centimeter wide, and 4 centimeters high. Okay. So that comes out about 12 cubic centimeters. So the mass would be what? 12 cubic centimeters times your 1.7 grams per centimeter. I get around 20 grams. You can do your own calculation. Okay. Now, what we want to do is we want to symbolize this, and we want to just look at a typical thin hoop cut out of this disk at some, in the vicinity of some radius. So we think of a ring of radius r and width delta r. Okay? Now that would be a ring maybe looking something like this. Okay? And the width is delta r, and the radius is r. Okay, well, what's the area of this thing? We'll work the thickness in a minute, but what's the area of this thing? Well, again, if we just slice the thing and straighten it out, it has a length equal to the circumference, which is 2 pi r, and a width of delta r, so its area is the length times the width, 2 pi r times delta r. And then if there's a thickness below that, a thickness of 2 centimeters plus 0.4 r, then we multiply that by the area of this thing and we get its volume. So that'll be 2 pi r delta r times the thickness, which is 2 centimeters plus 0.4 r. Then if the density is 1.7 grams per cubic centimeter, the mass is just this expression times our 1.7 grams per cubic centimeter. Then what's the moment of inertia? Well, the moment of inertia, all the mass is concentrated at or very near 5 centimeters from the center. So that entire mass is at that distance, so that the moment of inertia is just that mass times r squared. Now, I'm going to symbolize things a little bit. I'm going to kind of get rid of most of the numbers. I'm going to say the contribution to the area of the surface of this disk is 2 pi r times delta r. Okay, that's the area of the delta r increment at distance r. The volume corresponding to that area is just, well, you multiply the area by the thickness. Now, I didn't write the 2.2 centimeters here, but we want to keep in mind that that really is 2 centimeters. Okay. Then the mass contribution of that, of the material of the disk corresponding to this ring is what? It's density times delta V. Now, I just wrote down a delta for density, that's a lowercase delta, instead of the 1.7 grams per cubic centimeter, partly because it's more compact and I don't have a lot of room, but also partly because you don't necessarily have a constant density. Okay, this disk might change density as you move away from the center and might change density in some other way. So this density could be a function of position. In this case, it's a constant, but it could be a function. And if it's a function of r, then it fits into this scheme really well. Okay? And finally, the moment of inertia is just the mass of the thing times its distance, which is pretty constant for the whole mass, times the square of that distance. Okay? Mass times the square of the distance. So we should understand these relationships. Now, if we add up all of the volume elements, we get the total volume of the disk. So we would sum up all the 0.2 centimeters times plus 0.4 r times your delta A. Okay, and your delta A being this, that means you'd be summing up 2 plus 0.4 r multiplied by 2 pi r times delta r. And that's the expression we have here. So that would be the sum of all the volumes of, let's say, these very thin hoops. Okay? And that would be the total volume of the disk if you take that from the center out to the outer radius. The masses, well, you just multiply your deltas by your density delta by your delta V, and you have the mass of a given region, so you just add up all those. So you just multiply all your masses by delta, and you have the total mass. And of course, if delta happens to be a function of r, you're still going to do the same thing. Then to get your total moment of inertia, well, you've just got to add up all of those. The contribution from each is your delta, well, your mass, which is the delta times the volume, and I've underlined the volume in purple. So there's your mass times r squared. Okay? then you observe that, the total volume is the limiting value as delta R approaches 0 of the sum of all the volumes. Okay? And that limit is just the integral of this expression, except the R is replaced by dr, because your radius is, your delta R is approaching 0, it approaches a dr, and I'm waving my hands over that as physicists often do, and I don't call myself a physicist, I know a lot more mathematics, but so in a hand-waving explanation, we see that this expression approaches this integral, okay? There are details to the way Riemann sum, for example, approaches the integral, and we're not going to worry in this course about the final points of that. The main idea here is that if you have an expression for the volume of a single thin hoop within this thing, you can take that expression, and move it to an integral, okay? Then it can do the same thing with the masses. You can move this expression to an integral, okay? And you can see how the integral relates to the expression. And the same with the moment of inertia, okay? Of course, I've used an r cubed here, but that's my r times r squared. Now, any of these integrals is easy to do. Okay, it's just power functions. Here you're integrating a multiple of r and a multiple of r squared. Here you're integrating a multiple of r squared, of r cubed, and a multiple of r to the fourth, and so forth. Okay, so we get these integrals. We could easily do the integrals. We could easily complete this and get our moment of inertia.